Anomalous reflection of caustic spin wave, beams in a Magnonic Waveguide.
Hold on, so you're telling me that these spin wave beams are basically breaking the usual reflection rules? They don't just bounce straight back, they land on these special spots called caustic points, which you can think of as magnetic crossroads where everything changes in a precise way.
Exactly. And here's the kicker. When we look at them with time-resolved microscopy, it becomes clear that after hitting an edge, their new direction isn't about keeping tangential speed the same. It's all tied to where those special points sit on this curved energy landscape called the iso-frequency contour.
Okay, but what does stationary group velocity actually mean for how they move? And why would that flip our usual reflection expectations?
Great question. When we say the group velocity is stationary at these points, it means that if left alone, their natural path freezes in place. So when you hit an edge and send them back, they're not just bouncing, they jump from one caustic point to another, which totally upends the classic reflection picture.
So instead of angles matching like Snell's law says, these beams kind of slide into new directions based on this stationary condition?
Exactly. It's not about symmetry or equal tangential components anymore. The magnetic field acts like a knob you can turn to steer both incoming and reflected waves by nudging where those caustic points sit along the energy curve.
So if I'm following, changing the field angle basically rewrites how these beams behave at each reflection.
Right. You're controlling which special point they land on, and thus their new direction. It's like guiding them through an obstacle course where the walls can be reshaped by your input.
And this actually matters for building better magnonic circuits?
Absolutely, because now we have a way to steer these beams without traditional mirrors or complex geometries, just magnetic tuning and clever waveguide edge design. It opens up new avenues for reconfigurable beam steering that could be super useful in compact devices.
So you're saying this isn't just theoretical curiosity, it's a toolkit for engineers working with spin waves?
Right on. We've shown it works experimentally, and now the challenge is figuring out how to integrate these principles into scalable platforms where we can reliably predict and harness that caustic point behavior.
Sounds like we're watching a new kind of wave dance unfold right before our eyes. So let's dive into this part. I see a long list of papers cited here. Feels like a history lesson on magnetostatic wave beams and spin waves. Jamie, can you walk us through why all these studies matter for the current paper?
Sure thing. Think of each reference as a stepping stone that built up our understanding over decades. The 1988 Soviet Physics Journal piece laid early groundwork on how magnetic fields interact with wave beams, basically showing waves could reflect and refract in magnetic materials, which sounds simple, but was foundational.
Okay, so they were figuring out the basics of how waves behave inside magnets?
Exactly. Fast forward to 2014, researchers realized you could use these wave behaviors for something cool. They designed a special material called yttrium iron garnet film where spin waves, which are tiny magnetic ripples, could totally bounce off without any reflection at the edges.
Spin waves? Like magnetic versions of sound waves?
Spot on. Except these are quantum mechanical and tied to magnetism. The 2020 paper showed how you can control these spin waves in thin films, think sculpting magnetic ripple patterns with precision.
That's wild, but why so many papers about this?
Because each study tackled a piece of the puzzle. Some focused on perfect reflection, others on creating controlled edge effects, or even manipulating spin waves in tiny structures like nanoscale grooves. Imagine carving paths for magnetic ripples smaller than a human hair.
So they were basically testing different ways to control these wave patterns?
Right. And by 2023, people started seeing how these controlled spin waves could be used in tiny magnetic circuits, like building blocks of future devices that process information using magnetism instead of electricity.
So all this research eventually led to what? The current paper's focus?
Precisely. By understanding how wave patterns start, reflect, and propagate across different materials, researchers could design smarter systems that manipulate magnetic waves with incredible precision, just like directing light through lenses, but using magnetism instead.
That's actually pretty mind-blowing. So every paper here represents a piece of the big puzzle they solved?
Exactly. Each study, even if niche on its own, contributed to this larger understanding that now lets scientists engineer materials where spin waves behave exactly how we want. Think ultra-fast data storage or quantum computing components.
As we wrap up this fascinating journey through wave dynamics and magnetic engineering, let's reflect on what makes this discovery so transformative. The convergence of theoretical insight and experimental validation has not only expanded our fundamental knowledge, but also charted a practical path toward next-generation magnonic technologies. Imagine circuits where spin waves dance along precisely engineered pathways. This is no longer science fiction, but an emerging reality shaped by decades of interdisciplinary collaboration. The ripple effects will likely extend far beyond physics labs, influencing everything from ultra-dense memory devices to quantum information processors that harness the subtle choreography of magnetic ripples. As we close today's episode, remember innovation often springs from daring to question established norms, just like these beams defying conventional reflection laws. Until next time, keep wondering and stay curious.